Let's run through complete solutions to multiple choice problems 13 to 18 non-calculator on the released 2012 Calculus A/B exam. Now there are some pretty sneaky conceptual problems on here to do with viewing definite integrals as areas and the fundamental theorem of calculus. So please try not to get discouraged if you find these a bit tricky the first time through. I personally think problems 15 and 17 are the ones most likely to cause students difficulty, so let me know what you think. But let's dive in. In problem 15, we're given a definite integral of f of x, and we're asked to calculate it. Now, you're probably pretty well practiced at finding definite integrals using formulas, substitution techniques, that sort of thing. But here, the rule we've been given for f is a nasty looking piecewise function. So that kind of falls by the wayside and isn't that helpful for us. What we need to remember is that a definite integral can always be interpreted as an area. Unfortunately, this piecewise rule that I said is pretty nasty. If we graph it, we can actually understand the area under the graph, its definite integral, using geometric pieces that we understand pretty well. Let's see what I mean when I graph this function. So the rule changes at x equals 3. When x is less than 3, the rule for the function is just constant. We get a value of 2. And when x is greater than or equal to 3, the rule for the function is x minus 1. So that's a linear function with slope 1. When x equals 3, the y value is going to be 3 minus 1, 2. So this is actually going to be a nice continuous function. I can fill in that point there. So we want to know the area under this curve between 1 and 5. So let's say x equals 1 is there, and x equals 5 is there. Now, fortunately, I can break up this area into pieces that I understand pretty well. You can see I have a load of rectangles, squares, triangles, that sort of thing. So if I can figure out this area here, and this area here, and add it to this triangular area, that will give me the correct answer for my definite integral. Let's have a look at some of these side lengths. Well, I know this is side length 2, because it's 1 up to 3. This is side length 2, because it's 3 up to 5. This is side length 2, so that's actually a square. I also then have side length 2 here. And for my triangle, I have a base of 2. And well, over here, when x is 5, what is my rule for the function giving me? It's giving me 4. So that tells me I have another 2 there. So the integral, which is my area, is simply going to be the area of my yellow square, so that's 2 squared, plus the area of my blue square, that's also 2 squared, plus the area of my triangle, which will be a half, times the base, times the height, 2 and 2. So I get 4 plus 4 plus 2, which is 10. So the answer is D. Now, if you wanted to be super fancy, you could have thought of this square plus a triangle as a trapezoid and used the formula for a trapezoid. I don't want to ever have to remember the formula for a trapezoid if I don't have to. So, triangle plus square it is. In problem 14, we're asked to calculate the derivative of a composite function, f of g of x, when x equals 3. So when we see a composite function, we should be thinking almost certainly I'm going to use the chain rule. Now, there are a couple of different ways we could approach this. The first would be to actually figure out a formula, the rule for f of g of x, and then apply the chain rule to that formula. So f of g of x will be f of 3x minus 2. If I then substitute that into the rule for f, I get the square root of 3x minus 2 all squared minus 4. I would want to tidy that up a little bit before I apply the chain rule to it, but I could find a rule for the derivative of f of g of x and plug in x equals 3 to get my answer. But we can use the chain rule a little more directly here. And I think it's a little more simple to do it that way. And it tests that we're really comfortable with what the chain rule actually says rather than just procedurally carrying it out. Now here we can just procedurally carry it out, but the AP loves to design questions where you need to be really happy with the conceptual foundation. So let's see how we can use that here. So the chain rule says if I take the derivative of a composite function, what I'm supposed to do is take the derivative of the outer function f evaluated at the inner function and multiply by the derivative of the inner function evaluated at x. So in this problem, we want to know what happens when we evaluate this at x equals 3. So instead of x's, I'll just put 3's. And now I need to work out the pieces that will let me substitute in to get the answer here. So let's take them one at a time. So we need g of 3, right? That is this piece here. So the rule for g is just 3x minus 2. So if I substitute in x equals 3, I will get 7 for that first piece. I need to know g prime of 3. Well, g prime of x for any x is just 3 if I take the derivative of 3x minus 2. So in particular, that tells me that g prime of 3 is equal to 3. So I have this second piece here. So the final piece of the story that I need to work out is this f prime of g of 3 character. But we already figured out that g of 3 is 7. So if I can calculate what f prime of x is and substitute in x equals 7, I'll have the correct answer. So if I look at my rule for f of x, it's right here. I can think of that as x squared minus 4 to the 1/2. I need to take a derivative. This is also a composite function, so we'll also need the chain rule right here. So I will get the derivative of the outer function, which is 1/2 bracket to the minus 1/2, times the derivative of the inner function, which is 2x. Now I could tidy this up, but let's remember I'm not being asked to calculate f prime of x, I just want f prime of 7. So we may as well just substitute in straight away. So f prime of 7 will be, well, notice my 2 and my 2 do cancel, so I can do that a little bit of tidying. And then I will get 1 over the square root of 7 squared minus 4 times 7. If I tidy this up more, I get 7, over the square root of 49 minus 4, that is 45, but let's simplify that square root as 3 root 5, because 45 is 9 times 5. So now I can substitute in. So if I look at my different values, I have my f prime of 7 piece, that is 7 over 3 root 5. I have my g prime of 3 piece, that was just 3. Those 3's will cancel and give me the correct answer of 7 over root 5. Answer A. Problem 15 is that first conceptual problem that I said was on the trickier side. So let's pay close attention here. We're given the graph of a differentiable function, f. Here it's the blue curve. And we use it to cook up a new function, h of x. And we use a definite integral to cook up h of x, using what I call the area so far function. Because what this h of x does is, it starts at x equals 0. It picks some x that you want to evaluate at the function, and it just works out the area so far under the curve between 0 up to x. So if I want to calculate h of x, I need to know what that area is. Okay. And we've been asked to figure out the relationship between h of 6, h prime of 6, and h double prime of 6. So first and second derivatives all over the place at x equals 6. So first things first, let's think about h of 6. So when I plug x equals 6 into h, it tells me, actually, this x that I'm interested in, I'm going to move it all the way over here to be x equals 6. So that area so far that I want to calculate to figure out h of 6 is this entire area here. Okay, well, I have no idea what that area actually is, but I do know that it is entirely below the x-axis. So that means that the definite integral will see that as a negative area, a negative value. So whatever h of 6 is, it is negative. Okay, well, that's nice, I guess. But we know a little bit of information now about the relative size of one of these quantities, so we shouldn't complain too much. Let's now try to think about h prime of 6, or in general, h prime of x. Now remember, h is built as an integral, of f. We take f and we integrate it to get h of x. So the fundamental theorem of calculus says, if I take the derivative of h, that will just give me back my function, little f. Okay. So h prime of x is just the function f that I started with. So in particular, I'm interested in h prime of 6. So that's going to be f of 6. And I can read straight from the graph that when x is 6, f takes the value 0. Okay, we're getting somewhere, because I know that one of these quantities is 0, h prime of 6, and the other quantity is negative, h of 6. So I know something about the order of these quantities. We're making progress. Finally, let's think about the second derivative, h double prime. Well, if h prime is f, the derivative of h prime, to get me the second derivative, will be the first derivative of f. I'm just taking that equation and differentiating both sides. So that tells me that h double prime of x is f single prime of x. Okay, well, I want to know what h double prime of 6 is. So that is f prime of 6. Well, remember, f prime, the derivative of f, tells you when f is increasing and when f is decreasing. So at x equals 6, the function is increasing. As we look at the graph from left to right, the function is rising. So because f is increasing, that means its derivative will be positive. So now we can piece all this together to get the correct answer here. Okay? Because I know that my least quantity, h of 6, is negative. I then have, h prime of 6. Well, that was the quantity we figured out was 0. And finally, we just showed that h double prime of 6 is positive. So stringing all of this together, we get h of 6 is less than h prime of 6 is less than h double prime of 6. If we scan down our answer choices, we should see pretty quickly that is answer choice A. After that last one, problem 16 is going to seem pretty wham bam, so let's get to it. We're told that a particle is moving along the x-axis on some journey, maybe moving back and forth, doing something, who knows what. But we are told that the position at time t is given by this formula here. Okay, t minus a times t minus b. And we're asked, where a and b are constants, they're not equal, hooray. We're asked where the particle is at rest. Now, at rest means not moving. So this means we want the velocity of the particle to be 0, while the velocity is the derivative of position. So here we really are asking when x prime of t equals 0. So I need to take a derivative of this rule. I could be smart and use the product rule, because it's a product, so a linear factor times a linear factor. But I could also just expand out these brackets in a not very clever way to get this for my rule. So if I calculate x prime of t, I'll get 2t from that first term, minus a from the second term, minus b from the third term, and that constant term ab just differentiates to 0. So all we're trying to do is solve when this quantity is equal to 0. If we rearrange and solve for t, we will get a plus b all over 2, which is answer B. Nice. Problem 17 is sort of the partner in crime that I mentioned earlier to the tricky problem 15. And here we're cooking a function f up out of an unknown function and its graph. In problem 15, we're kind of doing the opposite to try and learn information. So we're told that the graph of this function f is this nice linear curve, and we're building it as a definite integral of some function g. Okay, we need to pick which of these graphs is plausibly able to be the graph of g. Now, you might just stare at this and have absolutely no idea how to start. And believe me, that is okay if that is the case. Sometimes that happens to me too. Here, though, let's try and get a foothold. So notice that when x is 2, okay, this area so far function that we met earlier is going to give me an answer of 0. Okay, because when I start at 2 and don't go anywhere, the area that my curve has swept out so far is nothing. It's just 0. So that means that this x-intercept is happening at x equals 2. Now let's look at what happens as we move to the right and we move to the left from x equals 2. So as I move to the right, you can see that my area, which is what f is measuring, this area so far, is increasing at a constant rate. Right? It's a linear function. That means constant rate. So we are increasing at a constant rate there, the area under the curve of g. So we can already rule out something like C, because as I move to the right, okay, this area that we're sweeping out is getting more and more and more. Okay, we were at the thin end of the wedge to begin with. But as we move over and over and over, we're getting more and more area as I move by the same amount. Okay? So it cannot be answer C. Okay? So as we're moving to the right, I get x, the area is increasing at a constant rate as I move to the left, the area is going to be decreasing, getting more negative at a constant rate. That's really just a trick of the fact that here, when x is less than 2, say it's 1, that looks a little bit weird because we usually have the limits of the integral going from smaller to larger. We can make sense of that integral, but we need to remember it's the negative of the one that we're used to seeing, with the smaller number as the lower limit. And so that is why the area, when I move left of 2, gets more negative. Okay. Well, I've been talking for a while about how this area, as I move to the left and right from 2, is growing at a constant rate. And so you can see it really has to be answer choice A, because every time I move a little bit over, I'm just getting another piece of the same size. Like, this area really is growing at a constant rate as x moves to the right and x moves to the left. So the correct answer is going to be A. We can see how it matches up there. But we also had to rule out B, because B is also increasing at a constant rate, the area under the curve. But because it is below the axis, its area is always going to be thought of as negative. Okay. So that's how we're able to rule out answer B. Answer D and answer E really aren't going to work out for the same reason that answer C didn't work out. The area is not increasing at a constant rate as I move beyond 2. It almost looks like it's showing some exponential growth, or exponential, the negative exponential growth. Okay. So the answer is A. If you had no idea how to start this, okay, how I would suggest you get into it is, notice that f, the function, is a linear function. So when I found f by integrating the function g, okay, I got a linear function. So we should be thinking, what kinds of functions, when I integrate them, do I get a linear function? Well, if you think about your standard derivatives and antiderivatives, power rule, all that good stuff, you know that if you integrate something and you end up with a linear function, you had to have started with a constant function to begin with. Okay. Think about if I integrate the constant function y equals 2. What I get is y equals 2x. It's a linear function, y equals 2x. So it was really always a case of which of A or B is going to be correct here. And we needed to do a little bit of analysis, a little bit of thought about what sign made most sense for f based on what the graph was looking like. Right, question 18, last question of the video. If we spot what's going on here, this one is so simple, so straightforward, so satisfying. So I guess let's hope we spot what's going on. This is a limit as h drops to 0 of this quotient. Now, if we screw up our eyes here and don't look too closely, it kind of looks like a limit of a difference quotient, right? Whenever we see limit as h drops to 0, that is a standard piece of notation that's kind of cluing us into what might be going on here. So if I take my h dropping to 0 definition of a derivative, right? This is, by definition, if the limit exists, what it means when we talk about f prime of a, where f is some function we're trying to take the derivative of. So this specific expression they've given us looks a whole lot like this one here. The key, the way into this problem is to figure out how to write this limit as a derivative that we know how to calculate in a different way. So looking at the comparison, it looks like A is 4, right? Wherever I see a 4, that's where I see an A in my difference quotient definition. What function am I looking at? Well, the only place I see a function here is ln. The only place I see a function here is f and f. So that suggests that the function that I want to be looking at is just the natural log function. Well, that's all there is to do it. It suggests that this limit is going to be f prime of 4, where f is the natural log function. Well, I know independently from all my memorizing of derivative tables that the derivative of ln of x is just 1 over x. So in particular, f prime of 4 is going to be 1 over 4. That's our final answer, B. So there we have it, another 6 problems in the bag. How did you get on? What did you think of 15, 17, the slightly more conceptual ones? Let me know in a comment. If you haven't seen some of my earlier videos where I've gone over the earlier problems, I'll drop them right here. And if you want to see the next set of problems, here they are.